So, welcome back for the final lecture of this week. So, we are talking about the problem of part-to-switch stacking, and the methods that we are discussing are generic methods for any sequence labeling task. So, input is a sequence like here sequence of the words, and output is again a sequence where for each word I want to predict what is the corresponding part-to-speech stack. So, we talked about hidden Markov models and also Maxent model. So, in general in Maxent model we talked about how do we use that simple classifier for a sequence labeling task. So, we call that the maximum entropy Markov model. Okay. And the formulation was very easy, that is you predict the tag for each word and then multiply the probabilities for the whole sequence. There was one problem though, that because we need the sequence of we need the tag of the previous word in certain features to assign the tag at this particular word, we will need to use beam search algorithm, and we also discussed what is the beam search algorithm. So, what I will do in this lecture, I will take an example where we will see how to use beam search algorithm, and then I will briefly discuss what are conditional random fields and how are they different from maximum entropy models. So, conditional random fields again is a very vast topic, we will not cover fully. We will only give you the hint that once you know Maxent or MEMM models, what are conditional random fields, how are they different from those. So, starting with a practice question. So, here, so we are having the same sentence, the light book, and you are given that for all the three words, the, light and book, the top two tags are determiner noun, verb adjective and verb noun. Okay. Now, you want to use your MEMM model. So, for a given tag or given word wi, you use particular context. What is the context here? The previous word, next word and the tag given to the previous word. This is the context. So, that means all your features will be defined over this context. So, here in this example, we have shown some sample, like you are given 8 different features, and now you have to use the beam search algorithm to find out what will be the appropriate tag sequence for the sentence. So, what are the features given? The features are simple, like the previous tag, the tag given to the previous word is determiner, and the current tag is adjective. Previous tag is noun, current tag is verb. Previous tag is adjective, current tag is noun. Previous word is the, current tag is adjective, and so on. Okay, and in the end you also have features like the next word is light, current tag is determiner, previous word is null, and current tag is noun. What it means is that the ith word will be starting the sentence. That's why the previous word will be null. So, now you are given these features, and for simplicity you are given that each feature has a uniform weight of 1. Now, your task is to use beam search algorithm with the beam size of 2. What do I mean by a beam size of 2? At any given point you will keep only the top 2 highest probability tag sequences, and everything else you will forget. So, at any point you will know what are the top 2 tag sequences till this point, and overall you have to find the highest probability tag sequence for the sentence, that is the light book. So, let us see how do we solve this. So, we are having 3 words in the sentence, the, light and book. Okay. The word the has 2 tags, 2 possible tags. It can be either a determiner or a noun. The word light can be a verb or an adjective, and the word book can be a verb or a noun. Okay. So, now how do we start? We have to find out probability tag I given wi, or instead of wi let me write the context xi or hi. There are different notations for that. So, here context is wi minus 1, wi plus 1 and previous tag. Okay. And now, what is the formulation of this tag I given the current word or current history here? It will be exponent summation lambda I fi, okay, and feature we know is a function of input and the tag, divide by z. and z is nothing but a normalization constant, so that all the tag probability will add up to 1. So let us try to do that. When the tag is determiner, word is the. Okay. So let me just write down exponent of summation lambda I fi, and lambda I is 1 here in this problem. So it will be simply exponent summation over fi. So what features are 1, what features are 0. So for this word, so everywhere where we need the previous tag or the previous word should be 0, because this is the start of the sentence. So I do not have any previous word tag or any previous word. So all these features value will become 0. Now what is the feature that will become 1? Possibly this one. This needs the next word, I plus 1th word is light, and the current tag is determiner. Is that will that be 1? So if you see here, current tag is determiner and the next word is light. So it will be 1. So that is for feature f8. So it is 1. So I will say it is exponent, or let me write e to the power 1. Yes, lambda is 1 divided by z. Let me find out z later. Let me find out the value for noun. So again, similar to this one, all the features from f1 to f6 will become 0, because we do not know what is the previous word or previous tag. This feature could have become 1, but the current tag is not determiner but noun, so this will also be 0. This feature, previous word is null, yes, that is true, is the start of the sentence, and the current tag is noun, this will also become 1. Okay, so this is the only feature that becomes 1 for noun. So this is e to the power 1, and what is the normalization? This plus this. Okay, so 2 times e to the power 1 divided by 2 times e to the power 1. So both will become 0.5. Okay, so fine. So at this point, all the two tags have both the tags have a probability 0.5, and here because I am using a beam size of 2, I will have to keep both these tags. So now I am keeping both these tags with probability 0.5, 0.5. Now let us go to the next word, light. Now again, so I have to use probability of verb given this history. Now the history is previous word, current word, next word, and the previous tag. So now when I am going about talking about verb, if I have to compute these features, I need to know what is the previous tag. Okay, here it can be either determiner or noun. So that's why I need to talk in terms of the sequences. So here I have one sequence, determiner noun, determiner verb, and second sequence with noun verb. So I have to take both the sequences separately and compute the probability. Similarly, I will have to do the same for adjective. Okay, so let us try to do that for one sequence, say noun verb sequence. Okay, so what will be the probability of tag I given the word? So this we can write here. So let me write only the summation lambda I fi part. So this will be summation lambda I fi. So let us go to the features here. So noun verb. So let us go to the features. First features, previous tag is determiner, no, previous tag is noun here, this is 0. Previous tag is noun, yes, and the current tag is verb. This is okay, this will be 1. So f2 is 1. f3 is 0 because previous tag is not adjective. f4, previous tag is the, no, yes, previous word is the, current tag is adjective, no, it is verb. Then this one is also not correct because the current tag is not adjective but verb. Previous word is light, no, next word is light, no, previous word is null, no. So only f2 is 1. So this will be, for this sequence, it will be e to the power 1 divided by the normalization z. Now what will this normalization depend on? This will depend on from everywhere where this context is taken, what are the probabilities. So I have to compute the probability for this one also to find out this z. Okay. So, I know this probability, I know this function, and I will normalize them to add to 1. So, what will be for the function for noun and adjective? Let us try that from the features again. Previous tag is determiner gone, previous tag is noun but current tag is verb, no, previous tag is adjective, no, previous word is the, yes, and tag is adjective, yes. So, this will become 1, F4 will become 1. Previous word is the, yes, next word is book, yes, current tag is adjective, this will also become 1, all 3 will be 0. So, now this will become e to the power 2 divided by z, and z I can write as e plus e square. Same here, e plus e square. Okay. So, now I know the probability of getting verb at this position given the previous tag is noun, and adjective at this position given the previous tag is noun. But what is the probability of this whole sequence? It will be multiplied by the probability of getting noun, that is half. Similarly here, half. Okay. So, this is the probability of selecting this sequence. Similarly, I will compute the probability of selecting this and this, normalize them, multiply by 0.5. So, now I will get the probability for 4 sequences. So, that is noun verb, determiner adjective, and noun adjective. I have the probability of a 4 sequence after this step, and then I will select only top 2 from there. Okay. So, suppose the top 2 could be say noun verb and determiner adjective. So, what will happen now? For the next step, I will consider only say determiner adjective and noun verb, and I will know also their probabilities. Then I will take each individual as a history and see, okay, determiner adjective, then noun, determiner adjective, then verb. Normalize the probability. Similarly, noun verb, noun, noun verb, verb. Normalize the probability. Accordingly, multiply this. So, again you will have 4 sequences here. You will have probability for all 4 sequences and take the one that is having the highest probability, and that will be your final tag sequence in this example. Okay. So, I hope the idea is clear. I am not solving this fully, but I will encourage you that you do it on your own and see that you can find out what is the appropriate sequence using the MEMM model. So, this was how to use beam search algorithm for MEMM model. Now, I will just talk briefly about what is the problem with this, what is the single problem with this maximum entropy model, so that we have to think about conditional random fields. So, in maximum entropy model, we do a per state normalization, that is, all the mass that arrives at a state must be distributed among the possible successor states, and this is giving rise to a label bias problem. Okay. So, let us see what is the intuition. So, what do I mean by this? So, let me take the same example. So, first let me take the same example to explain what do I mean by normalization at each state. So, take this one. Okay. So, you are computing noun verb and noun adjective, okay, and you had the features like e square and e1, but you are normalizing them by, so you are normalizing them such that these two add up to 1. Same thing you will do with determiner. You will make sure that these two add up to 1. So, you are normalizing at each state. Okay. So, why will that be a problem? So, let me just take an hypothetical example. So, suppose in your maximum entropy model, you are having a tag T1 and tag T2 at any given point. Now, next point, suppose from T1 you can go to 2 different tags, T1 prime and T1 double prime, and from T2 again you can go to T2 prime, T2 double prime. They may be same, they may not be same. Now, how do we compute this probability? It will be e to the power summation lambda I fi divided by z. Z is nothing but the addition of these two. Same here. Now this is what is the importance, how many features you are having and so on. Suppose for a particular choice of these tags, it happens that in one of the branch you are having this value as 0.002, okay, and this value as 0.0001, okay, or let us say or even much smaller value. And this branch is having value of 0.03, 0.04. So what will happen now? This is not normalized values, okay. So it tells that the summation lambda fi is getting a higher score in these two cases and lower score in these two cases. But because you are doing per state normalization, you will divide it by 0.002 plus 0.0001, and that will be close to, say, very close to 1, maybe 0.98 or something. Okay. On the other hand, this will be close to 0.45 or 0.55. So what is happening here? Even though this probability was low, when I normalized, this became very high. That is one particular problem. On the other hand, suppose that from T1 there was no possibility of going to T1 double prime. So there was only one tag possible. So you will, independent of the context, it will always get a probability of 1 because you have to normalize at each state. So that is, if from T1 I can only go to one tag T1 prime and everything else has a probability of 0, because of normalization this will become 1. So we multiply this probability by 1 independent of the context, and this is called as the label bias problem. And this comes because you are normalizing at each step. So that is one problem with the maximum entropy Markov models. So let us see how we avoid this problem in conditional random fields. So I hope this problem is clear, that you are doing normalization at each step, at each state, and that is giving some bias towards those states that are having fewer transitions than the states who are having more number of transitions. Okay. So let me just tell you one thing. So suppose I have two different tags. From T1 you have 2 possible transitions, but from T2 you have 5 possible transitions. So what will happen? These will get there will be a bias towards choosing this state, because this will be normalized and one of these will get a higher value, and this may not happen here because there are 5 possible transitions. So this gets a bias, and that is not what is ideal. So how do we avoid this problem in conditional random fields? So conditional random fields are undirected graphical models, and while there are many variations of conditional random fields, so there is a generic structure, we will look at the linear chain structure. So here we are seeing the linear chain structure of conditional random fields. So again, like in the previous case, you are having a sequence x1 to xn, and these are the tags y1 to yn assigned to these tags. Now how they are, so in what way they are very similar to maximum entropy model? They are similar in the sense that they use the same sort of feature functions. So what we are seeing here, for the ith point, the feature function, so suppose I is equal to 3, would be a function over the previous tag y2, current tag y3, the input, you can take any number of words before and after x3, and this is the ith index. Okay. So feature functions are again function of the input, current tag and previous tag. This is in the linear chain structure. So conditional random field are like factor graphs. So what happens? The probability of each node will depend on only its neighbor. Okay. So, and you can use the same sort of features. So, like, so this is what we had discussed in maximum entry model also. So, I have a feature that is 1 if previous tag is IN, current tag is NNP, and the current word is September, and 0 otherwise. So, you see they are very similar sort of functions that we are using in maxent. So they are same as maxent in that sense, but how they are different? So, the difference comes in how the normalization is done. In maxent model or maximum entropy Markov model, we are doing normalization for each state. Okay, so that is at each state, if I have multiple transitions, I will make sure that the probability for them adds up to 1. This does not happen in conditional random fields. So, we will compute the features expectations of feature values for each possible transition whole sequence, and then I will do normalization. So, that you can see from the probability function here. So, y is a whole sequence y1 to yn given the current input sequence x1 to xn, and lambda is the feature weights that you will learn. And this is 1 by ZX, so you are seeing a single normalization parameter exponent summation over I is equal to 1 to n summation j lambda j fj. Okay. So, let us try to understand quickly what this function means. So, you are having 1 upon ZX exponent summation I is equal to 1 to n summation over j lambda j fj, and fj is the jth feature, and this is probability y given x lambda. Lambda are the feature weights. Now, let us try to understand this. Now, what do I mean by y? Y is a sequence y1 to yn, and x is the input sequence, and there are many such sequences possible. So, this is the probability for a given sequence, and this z is a normalization that is done over all. So, that is the summation over all the sequences. So, you can write it as so this will be summation over all the sequences. I have this value for only sequence y, current sequence y, I will add it over all the sequences, that will give me z. So, summation over all y, possible y, exp, and whatever was inside. So, now how do we get this equation? So, remember this equation summation j lambda j fj, that is for a particular tag yj given at the a particular tag given at the ith position. Okay. So, I have exponent summation j lambda j fj, that is probability of a tag yi given xi. Xi can be all history at the given point. Divided by z was there, but forget about the z right now. Now, here we are computing probability for the whole sequence yi I is equal to 1 to n. So, this will be multiplication. So, multiply I is equal to 1 to n. So, multiply I is equal to 1 to n. So, now if I am multiplying multiple exponent, this is like so for example, e to the power x times e to the power y becomes e to the power x plus y. So, that is multiplication of all the exponent is nothing but like summation of what is inside, exponent summation I is equal to 1 to n summation j lambda j fj. Okay. And that is the function here, and zx is normalization over all such transitions, all such sequences. So, you are not doing normalization here. So, what happens in maxent? You are doing normalization here. So, for a given I, you make sure that everything adds up to 1, and that is not being done here. You are not making sure that at each I all the tags the probability for all the tags will add up to 1. No, you are doing a normalization only in the end. I know the probability or something that is proportional to probability for each tag sequence, and then I will normalize everything by this zx. and that's where this avoids the label bias problem. So this is the particular function that is used in conditional random fields. So what we can see that, so conditional random fields have the advantage of maximum entropy Markov model. They use the same sort of features. The kind of model is very similar to maximum entropy Markov model, but they avoid the label bias problem. So CRFs are globally normalized, whereas MEMMs are locally normalized. So that we had discussed, and they are very widely used and applied for many sequence labeling tasks. And so they were very close to the state of the art models for many of these sequence labeling tasks. So whatever sequence labeling task that comes to your mind, so starting from part of speech tagging to named entity recognition, so there you can apply a conditional random field model. And a lot of libraries are also available. So Mallet is one particular library that is very popular, and then there are CRF++ and many other libraries that you can use. What is important is that you understand what is the sort of features that you need to use, okay, and then the model will help you to train your own CRF. So this ends our discussion on part of speech tagging. We discussed a lot about what will be the models for sequence tagging. So now, from the next week, we will start discussion on syntax. That how do we find out what are the word arrangement in a sentence, and how do we group them in various sort of phrases. So I'll see you next week.